Space science is one of those fields that allows people to dive into almost any specialty and still find a way to contribute. In this episode, we bring you the results from astronomers, geoscientists, climate scientists, imaging scientists, glaciologists, meteorologists, planetary scientists, engineers, and even bioarchaeologists. This diversity of people is allowing us to better understand our world and beyond. In our first segment, we're going to look at how our ecosystem and past cultures have rebounded after prior naturally occurring climate events. It's unclear if this research will help us better recover from the climate change we're currently facing, but maybe it will at least give us hope and a starting point. From our world, we travel outward, looking at the meteorology of Mars, future technology for space exploration, and the star catalogs that will help us define our place in space. I always like to follow climate science with a look out to the far corners of our galaxy and beyond. We'll also be joined by Aerospace correspondent Eric Mattis to talk about this week's launches, and we'll look back at some of NASA's greatest January successes. We have all of this and more right here at Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. With the beginning of the year, many of us have set goals for ourselves. Eat better, recycle more, save for retirement. It's this last one that has led me to a phrase we don't see all that often in science. Past performance is no guarantee of future results. In science, past performance should exactly match future performance. And if it doesn't, averaged over multiple measurements, well, if we can't repeat our results, it means we don't understand all the variables that are having some sort of an effect. Most of the time, the science we report here on EVSN will have no impact on our human lives. It doesn't matter if red dwarf stars form more or less in different environments, or that Mars has stadium-sized dirt devils. These are amazing things, and we're going to talk about them more in the next segment, but while they may be intellectually fascinating, they aren't going to affect the price of eggs. Sometimes, though, just sometimes, the fact that we live on a planet is going to bring our lives and this show's science together for a segment. Today, this is the Earth Science segment, and we're going to take a scientific look at how our own world is changing over the centuries and millennia. And through the lens of science, we're going to see what these changes have to teach us about our world and maybe even our future. Consider for a moment mass extinctions. We know that at least one massive asteroid is responsible for one mass extinction. About 66 million years ago, a 10 to 15 kilometer rock from space hit our planet and wiped out all the large dinosaurs. Today, we are building sequentially larger and more watchful telescope networks with the goal of spotting any incoming space rocks with ample time to try and divert them. Not all forms of mass extinction are so theoretically easy to prevent, however. Turning back the clocks a little bit more, there was another mass extinction about 100 million years ago that is responsible for killing off most ichthyosaurs and pliosaurs, as well as 27% of the ocean's invertebrates, including stuff like mollusks and planktons. For many cultures and many more animals and other life forms, our ocean is the base of the food chain. Kill off the ocean and a lot of the food chain is lost. And that event, the ocean anoxic event 2, appears to have been caused by massive underwater volcanic eruptions. Massive is a bit of an understatement. This particular event may have been responsible for forming the large Eastern Pacific oceanic plateau that spans between North and South American plates. The processes that created that landmass, or I guess seafloor mass, well, they also released a lot of gases, including carbon dioxide, and depleted the ocean of dissolved oxygen, making the ocean anoxic. Just like a fish tank that doesn't have a bubbler or plants may not be able to support fish, an anoxic ocean can't support a lot of life. While the linkage between volcanism and the ocean anoxic event has been suspected for 40 years, the real impact has just been measured. In a paper led by Northwestern University's Matthew Jones, researchers obtained deep-sea core samples as well as other samples of ancient seabeds. These samples show a long history of calcium carbonate minerals building up and then a stark absence of this mineral during the event. According to Jones, quote, "This section of the core is visibly darker. It jumped right out at us. The carbonate either dissolved at the sea floor or fewer organisms were making calcium carbonate shells in the surface water." End quote. Carbon dioxide dissolved into seawater is a weak acid that can dissolve carbonates. By itself, this isn't enough to confirm volcanism. That would require one more piece of evidence. Coincident with this lack of calcium carbonate, Jones and his team also discovered a layer of osmium rich in the kind of osmium isotopes found in the Earth's mantle. This indicates that something, like a volcano, had to spew the osmium from in the Earth to into the ocean. Initially, the ocean wasn't entirely a deadly wasteland. However, the chemical changes were enough to stress out more fragile life forms. In the second research paper, led by Northwestern's Gabriela Kitch, researchers looked at fossil shells from the beginning of the mass extinction. Long before the death of pliosaurs was the death of planktons, including shelled unicellular organisms. In ideal circumstances, these shells are elegantly spiraled. But under stress, the shells decrease in size, vary in chamber number, and sometimes even reverse their spiral. Chemical analysis of the malformed shells found the calcium isotopic ratios were consistent with acidification. As these stressed critters in the upper ocean died, they sank and were consumed by microbes that released yet more carbon dioxide, driving the continued acidification. Plankton are a major source of oxygen, and their absence further limits the oxygen in the water. From there, mass extinction. According to a collaborator on both papers, Brad Sageman, these major carbon dioxide emission events in Earth's history provide the best examples we have of how the Earth system responds to very large inputs of carbon dioxide. This work has fundamental applicability to our understanding of the climate system and our ability to predict what will happen in the future." End quote. Currently, we may be experiencing the Earth's sixth great mass extinction. This time, the ocean acidification isn't being caused by volcanoes. It's more related to us. Once again, we're seeing massive areas of the ocean that have died off and appear anoxic. Maybe, just maybe, understanding this past event will make it possible for us to fast-track our modern ocean's recovery. Mass extinction has made for some great movies and books, but it is a lot harder to think about when it might be impacting us. This has many researchers looking for hope in history. I have to admit, I learned a new word working on this story: bio-archaeology. Folks who do bioarchaeology study human remains to understand past history. A newly published paper in the Proceedings of the National Academy of Sciences uses bioarchaeology to look at how humans have adapted to major climate events over the past 5,000 years. This research, led by Gwen Robin-Skugg of UNC Greensboro, brought together 25 authors from 21 universities who looked at societies from North and South America, the UK, Africa, the Middle East, and Asia. In every corner of the world, environmental changes at some point have changed what it takes for a group of people to thrive. While every crisis has to be dealt with in its own way, this paper found certain universal truths. Some things are just always bad. For instance, increased reliance on agriculture. Other things seem to always be a positive, like combining herding, farming, fishing, and other diverse food sources. How societies organize themselves is also important. Hierarchical urban societies weren't able to rapidly respond to change. The more economic inequality was present, the higher the risk of diseases and violence. According to Robin-Skugg, quote, "Diseases and violence spread. If you want to protect a society, large segments of a population cannot be left vulnerable." End quote. While historically cities with class disparity fared poorly, small interconnected rural communities that relied on local resources were more resilient. The future will require change. If we are to learn from history, then we need to reshape our reality. According to Robin-Skugg, successful strategies will support rural livelihoods, encourage diverse practices for obtaining food and other resources, foster equitable distribution, retain our capacity to mobilize when circumstances require, and encourage mutually beneficial relationships among groups and species. End quote. Whether we like it or not, our climate is changing. The 2015 Paris Agreement committed the signatory countries to keeping the global average temperature from rising 2 degrees Celsius over pre-industrial levels, with a goal of 1.5 degrees Celsius being recognized as what is actually needed if we want to keep the world we have from becoming a world a whole lot less livable. The thing about averages is you may have some places that oddly get colder somehow, and you may have some places that get a whole lot hotter, but the average itself only changes a little. New research is finding Greenland is one of those places that is getting a whole lot hotter. At the high elevations of the Greenland ice sheet, the years 2001 to 2011 were 1.5 degrees Celsius warmer than they were in the 20th century and represent the warmest decade in the last 1,000 years. Wide-scale melting is being observed, and kids born today can expect to see the melting of Greenland's ice sheet raising ocean levels by 50 centimeters, half a yard, by 2100. This is real. This is now. This is our world dramatically changing in our lifetime. Earth science may be part of why I like to study distant stars. After a break, we'll be escaping this world to look at things far more distant, including billions of new objects cataloged in our own galaxy. Later on, we'll even look at future tech that is going to help us build energy-harnessing spacecraft. Stay tuned. "18 years ago, on January 24th, 2004, the Opportunity rover landed on Mars. I distinctly remember that day because it was blisteringly cold in Boston, where I lived, and Opportunity was having a warmer day than I was. Mars is a world that is tantalizingly close to being able to support life as we know it. Today, we see multiple nations and space programs working toward one day landing humans on the red planet. Part of preparing for that future includes understanding Mars' weather and the dust storms that are responsible for ending the lives of so many solar-powered rovers and landers. The newest NASA rover to land on Mars, Perseverance, was equipped with a meteorological instrument, the Mars Environmental Dynamics Analyzer. The weather data from Percy's first Martian year has now been published, allowing us to see the highs and lows of living on the Martian equator. Led by Jose Antonio Rodriguez Manfredi, Manuel de la Torre Juarez, and Agustin Sanchez La Vega, this work shows how temperatures and pressures vary from day to night and season to season. Averaged out, the temperature at Jezero Crater is minus 55 degrees Celsius. While this is admittedly warmer than winter daytime temps in Antarctica or Yakutsk, Siberia, the highs and lows around this average are uniquely Martian. The warmest days can reach as high as 12 degrees Celsius or 54 degrees Fahrenheit, and the coldest nights plunge down to nearly minus 90 Celsius or minus 130 degrees Fahrenheit. On any given day, temperatures will rise and fall by 50 to 60 degrees Celsius, and this kind of a swing will bring with it turbulent daytime winds and dust devils that look more like small tornadoes in size. According to team member Ricardo Hueso, quote, "The dust devils are more abundant at Jezero than elsewhere on Mars and can be very large, forming whirlwinds more than 100 meters in diameter." End quote. Imagine a dust devil able to consume an entire football field. Stirring up dust is one of Mars' meteorological specialties. In January 2022, Percy encountered its first dust storm. This rover is powered by the heat from a radioactive source, a radioisotope thermoelectric generator, and it can stay powered up through the worst weather Mars has to offer. That storm's passage over the rover led to abrupt changes in temperatures and pressures, accompanied by strong gusts of wind, which kicked up dust and hit the instruments, damaging one of the wind sensors. While Mars doesn't actually have the will knock over a spacecraft style storms that set up the plot of The Martian, the wind sensor wrecking accident shows that we're going to need to design future missions and habitats to survive flying debris and wind abrasion. As for astronauts, here's to hoping they will get to stay inside and listen to the sand against their habitat while they stay warm and unbuffeted inside. Some kind of spacesuit will be required on the Martian surface, and astronauts won't need to fear the cold. But having experience driving snow during nor'easters, I don't wish driven sand on anyone. Mars, despite resembling areas of the American Southwest, is still a deadly frontier. Our ability to understand the universe is currently driven by technological advances. With each new Mars rover and each new terrestrial telescope, we can see more and learn more. As we'll discuss more in the last segment of the show, the earliest known star maps were created by Greek astronomer Hipparchus 2,100 years ago. From his hand-drawn maps sketched on papyrus, we've gone from cataloging a few thousand stars in our galaxy to billions of objects using the latest digital cameras. On January 18th, the National Optical and Infrared Laboratory, or NORLab, released the Dark Energy Camera Plane Survey. Funded by the Department of Energy, this camera produced 1 terabyte of data from 21,400 exposures that included 3.32 billion objects. The survey itself was funded by the National Science Foundation, and its images covered the galactic plane as seen from the southern hemisphere by the Blanco 4-meter telescope. From our perspective inside the Milky Way galaxy, the galactic plane is home to a rich mix of stars and dust. In all directions, our view is affected by diffuse nebulae that block some or all of the light from background stars, and the density of stars themselves can make it hard to tell where the light from one object starts and from another one ends. This survey looked at the sky in the near infrared and was able to peer through some of that dust. By combining these dust-piercing longer wavelengths of light with a sensitive camera and a large telescope, researchers were able to separately resolve stars. As described by NSF's Deborah Fisher, quote, "This is quite a technical feat. Imagine a group photo of over 3 billion people and every single individual is recognizable. Astronomers will be poring over this detailed portrait of more than 3 billion stars in the Milky Way for decades to come. This is a fantastic example of what partnerships across federal agencies can achieve." End quote. This Southern Hemisphere survey extends work already done by pan-stars in the Northern Hemisphere. Together, these catalogs provide one of the most complete catalogs of our galaxy. There are lots of different ways to survey the sky, and they're all constrained by one factor: time. Some surveys try to image as much of the sky as is visible, and no one image can see very deep. These surveys tell us about the region around our solar system and the distribution of the brightest objects. Other surveys look at a small region of the sky for a long period of time, and in that small postage stamp on the sky, we can see even faint stars out to large distances. The Dark Energy Camera Plane Survey walked the line between these extremes, looking at part of the sky for a reasonably long time. Exactly how a survey is performed is based on what researchers are trying to discover. Using a survey conducted by the National Astronomical Observatories of the Chinese Academy of Sciences 4.9-meter Guoshujing telescope, researchers measured the chemical composition of 93,000 red dwarf stars to see if star formation varies based on the ingredients going into the stars. Red dwarf stars are extremely long-lived, and any red dwarfs that have been formed should still be out there shining. Stars form as giant molecular clouds of material collapse and fragment. In general, these clouds will form a few massive stars and a myriad of smaller stars. It had been believed that the number of stars formed of different sizes, scientifically referred to as the initial mass function, should remain constant from cloud to cloud and eon to eon. That assumption, however, appears to have been wrong. In a paper published in the journal Nature and led by Lu Xiao, researchers document that red dwarf stars form in larger numbers in systems with more heavy elements. This new understanding is going to force us to change how we see the universe's stellar population evolving over time. When our universe first formed, it was made almost entirely out of hydrogen and helium. The first generation of stars that lived made heavier elements in their cores, and in their eventual supernova explosions, they spread that material, making it possible for the next generation of stars to form from some heavier elements. With each round of star formation, our universe has gotten a bit more chemically enriched. And now we know it has also gotten a bit more likely to form smaller stars. This change means we need to rethink how bright ancient galaxies should appear and just how quickly our universe was made more chemically diverse, one dead star at a time. This is your reminder. To get stardust into circulation, big old stars must die because the little ones are just going to sit there shining forever. Yes, you and I are made of stardust. We are made of massive stars' dust. Little stars? Well, they keep the bulk of their material to themselves. Oh, and I just want to take a moment to point out just the awesomeness of the art produced with this research. Every culture has its own way of visualizing data. And in this illustration by Wu Kan, we see the telescope in the lower right and an artistic figure in the sky. Each ring in this diagram represents a different epoch of star formation, and we can graphically see how the population of small red circles representing the red dwarf stars increases with each new ring. I have to admit, I wouldn't have understood the graphic without a caption. But once I understood it, I kind of love it. Anyways, with our increased understanding of the wheres and when of star formation, we are also coming to terms with the fact that the majority of these stars may have their own planets. Red dwarf stars in particular often have multiple planets per system. Someday, we hope to be easily able to look at these distant worlds and know if they have life. Right now, we don't actually know if that will be possible. Right now, in fact, we're still struggling to understand if there is life in our solar system on worlds other than Earth. On our planet, searching for life is easy. You go out, you scoop up a sample of dirt or liquid, and process it in a large laboratory that has powerful microscopes and highly sensitive mass spectrometers. If there is life, it will likely be both seen and detected from its organic molecules. Detecting life using a spacecraft is a bit more difficult. Spacecraft must be lightweight to get off our planet and out to other worlds, and they generally have very limited power. We can't just send our favorite microscopes and mass spec machines to Mars. Luckily, NASA is continually investing in the development of smaller, more energy-efficient devices, and a team from the University of Maryland has now created a 17-pound instrument that uses an ultraviolet laser to blast small samples off of rocks and a high-quality analyzer that can reveal the sample's chemistry. A description of this instrument published in Nature Astronomy details how this new tool will make the search for life a little bit easier for robotic explorers. According to lead author Ricardo Avallo, quote, "The good thing about a laser source is that anything that can be ionized can be analyzed. If we shoot our laser beam at an ice sample, we should be able to characterize the composition of the ice and see biosignatures in it." End quote. The sound of science just might be an almighty zot. After the break, we're going to take a closer look at asteroids, their homes in our solar system, and how they can both carry life and kill life, like those poor dinosaurs. Stay tuned. Some of the most unassuming objects in our solar system live the most dramatic lives. We're all accustomed to flashy images of Jupiter and its storms, Saturn and its rings, and even Pluto with its heart. Asteroids, the leftover rubble of our solar system's formation, these boring-looking objects may be where the action is really at. Today, the asteroid belt contains the highest density of rocky objects in our solar system. But asteroids can be found scattered just about everywhere. The smallest of these space rocks hold clues to our solar system's original ingredients list and the story of its formation. In 2014 and 2016, two very special missions were sent to grab asteroid samples and return them to Earth. The first mission, JAXA's Hayabusa 2, returned a sample of the larger asteroid, Ryugu, in 2020. And later this year, NASA's OSIRIS-REx mission will return its sample of Bennu. Both these asteroids have orbits that bring them in and out of the Earth's orbit, and they are small, just 0.5 kilometer and 1 kilometer in size. Their rubble pile natures make it pretty clear both these objects are the shattered remains of other, larger asteroids, or maybe they are the knocked off pieces of larger asteroids, or both. The answer is probably both. And since we have samples of Ryugu, researchers are now working hard in labs around the world to understand exactly what this rubble pile's history might be. Results from one of those studies has just been published in the journal Nature Astronomy by a team led by UCLA's Caitlin McCain. Ryugu is a carbon-rich, carbonaceous asteroid. By studying the isotopes of carbon and oxygen and the manganese and chromium ratios from radioactive decay, this team was able to determine that the source of their sample formed in the outer solar system within its first 1.8 million years. The object that formed must have been less than 20 kilometers across. If it had been bigger, they would have seen evidence of geologic processes, including melting and separations of metals and silicates. The minerals found in the sample are also consistent with the original asteroid's chemistry, being driven in part by interactions between ices and other materials. How that original object was shattered and exactly how it moved from the icy regions of the solar system to our warmer area? We don't know either of those things, but with data on what must have happened, we can now start to understand the hows and whys of it happening. Trying to understand how our solar system acquired its current shape is an ongoing problem in planetary science. We know that the places we see planets today don't match with where they formed. To wind back the solar system's motion, complex computer models have to explore a lot of, well, what if, to see exactly what starting positions can eventually produce what we see. This is not easy work, and every little observation has to somehow be matched. And one of the weirder observations to match is the distribution of asteroids in orbits near Jupiter. Called the Trojan asteroids, these pile-ups of rock are located 60 degrees in front of and behind Jupiter in its orbit. These locations are gravitational sweet spots called Lagrange points, and they allow objects to balance between the gravity of the Sun and Jupiter. Seeing objects at this large a distance isn't easy. The largest of these Trojan asteroids, 624 Hector, is just 225 kilometers across. And the vast majority of objects are just a few kilometers to a few tens of kilometers in size. Weirdly, there are significantly more objects in the leading L4 Trojan swarm than in the trailing swarm, L5. As things orbit today, both locations are equally stable and equally survivable. This means something in the past had to create the discrepancy. In a new paper in Astronomy and Astrophysics, researchers led by Jian Li found that if Jupiter started out closer to the Sun and the Trojan asteroids were gathered up early in the solar system's history, a high-speed migration outwards could have caused L5 to be less stable. According to Li, quote, fast migration of Jupiter can distort the configuration of the Trojan swarms, resulting in more stable orbits in the L4 swarm than in the L5 one. This mechanism, which temporarily induced different evolution paths for the two asteroid groups, provides a new and natural explanation for the unbiased observation that the L4 asteroids are about 1.6 times more than the asteroids in the L5 swarm. End quote. The Trojan asteroids are one of the most unexplored parts of our solar system, but not for long. On October 16, 2021, NASA launched the Lucy mission on a many-year journey to visit asteroids in both L4 and L5. To get there, Lucy will take a gravitational assist from Earth in 2024. On its way out, Lucy will visit the main belt asteroid, 52246 Donald Johnson, which is named after the paleoanthropologist who found the oldest humanoid fossil, Lucy. Currently, Dr. Johnson is still alive and just 79 years old. I, for one, hope that he will still be around when the first up-close images of his namesake asteroid make it back to Earth. In 2027 and 2028, Lucy will explore multiple objects at L4. We'll get another visit from Lucy in 2030, and then in 2033, Lucy will begin her exploration of L5. It is hoped that the mission will stay healthy and be able to add additional targets over time. It's truly remarkable that we have the ability to send missions out to the Trojan asteroids and to even bring back samples from closer in asteroids. Still, these missions cost a lot of money, and we just can't get as many samples back to Earth as we'd like. Luckily, the solar system likes to send us samples in the form of meteorites. Every year, about 40,000 metric tons of material, mostly dust, rains down on Earth from space. Mixed in with the dust will be a variety of rocks, and for every area the size of Texas or France, about 5 1-kilometer rocks will make it to the surface of the planet. Most of these rocks will end up in oceans and waterways. Others will strike in forests, swamps, and other lush areas that make finding meteorites nearly impossible. Still others will get found, often thanks to the help of security and dashcam videos that allow researchers to track down specific impactors. But if we had to rely on the video to locate every meteorite we have to study, we wouldn't have a lot of rocks. Luckily, we have Antarctica, which is a sentence I don't get to say nearly often enough. Over the millennia, rocks have continually rained down onto the ice, where they have remained either on the surface or buried under layers of glacier ice and snow. Each year, scientists and adventure-seeking volunteers travel to Antarctica to explore ice fields and the terminus of glaciers to collect meteorites. The cold, dry air of Antarctica is one of the best natural storage sites for these rocks, and their often dark surfaces are easy to spot on the bright ice. Some of these rocks were blasted off the surface of the Moon or Mars during impacts of those worlds, and others are shrapnel from collisions experienced by Vesta, Ceres, and other main belt asteroids. These rocks, they come from just about everywhere, and each one offers us a chance to study the kinds of gases and other materials trapped inside the mineral structures of other worlds. Most of the meteorites are small, the size of a fist or even smaller, but occasionally someone gets lucky. Researchers returning from the summer 22-23 season in Antarctica brought back a 17-pound meteorite. According to Maria Valdez, a research scientist from the Field Museum in the University of Chicago, only about 100 or so of the roughly 45,000 meteorites collected from Antarctica have been this size or larger. This particular space rock will go to the Royal Belgian Institute of Natural Sciences for analysis. If you would like to volunteer as an Antarctic meteorite hunter, instructions are on the Antarctic Search for Meteorites program website, which we'll link to from EVSN.tv. Be prepared. You'll need to write a paper, and if accepted, you'll be tent camping in temperatures well below freezing. But you'll be doing it for science. After the break, we'll be back with what may be the weirdest science story of the show. That's it. That's all I'm going to tell you. You're just going to have to stay put to find out what happened. And to also hear about This Week in Aerospace with Eric Mattis. Stay tuned. Earlier in the show, we talked about some of the amazing catalogs of stars and other objects that are being created today. In general, astronomy isn't an experimental science. We're an observational science. And our understanding comes from looking up, recording what we see, and then trying to make sense of those observations with maths and physics. The very first catalog to shape Western and Arabic thinking was created by the Greek astronomer Hipparchus of Nicaea in the 2nd century before Common Era. Hipparchus was one of the true greats of science. He's the founder of trigonometry, was the first to accurately model the motions of the sun and moon, and he created one of the first star catalogs. Containing roughly 850 stars with carefully measured positions and constellation boundaries, his catalog was foundational in later works, such as Claudius Ptolemy's star catalog, the Almagest, and in a Latin translation of Aratus's astronomical poem, referred to as Latin Aratia. Until recently, however, no copies of Hipparchus's original work were known to have survived. Remarkably, a fragment of this catalog has been found hidden beneath ancient religious texts purchased by Hobby Lobby for the Museum of the Bible in Oklahoma City. Let me say that again. Fragments of the Hipparchus star catalog were found beneath religious texts purchased by Hobby Lobby for the Museum of the Bible in Oklahoma City, referred to as the Codex Clamasi Rescriptus. The manuscripts date back to the 6th century and later, but they are written on reused papyrus. Recovered from St. Catherine's Monastery at the foot of Mount Sinai, these texts are now part of the largest privately owned collection of biblical texts and artifacts. In 2016, a selection of these documents were sent to researchers at Rochester Institute of Technology, who specialize in reconstructing text and images that have been overwritten. Papyrus isn't an easy material to create, and it was and remains expensive. Rather than use a new scroll for every new document, monasteries and other centers of learning would often scrape text from old papyrus and just reuse them. While the bulk of the original inks may have been removed in this process, indentations and some residue often remained. RIT's Professor Roger Easton is an expert in using multispectral imaging to reveal all traces of prior texts, and his work has been used to recover writing from the Dead Sea Scrolls, to find the oldest copies of text by Archimedes, and more. In looking through the Codex Clamasi Rescriptus, Easton and his students didn't anticipate they'd find any graphics, let alone such an important illustration of our sky. A new analysis of this discovery has been published in a pair of papers led by Victor Ginsburg and Peter Williams. They find the revealed text matches excerpts of Hipparchus's work in Latin Arietaea and is consistently of higher quality, with star measurements having an accuracy of better than 1 degree. This makes it clear that Hipparchus's catalog would have been more accurate than Ptolemy's, and makes it clear Ptolemy combined data from many sources, and not all were on par with Hipparchus's original work. The field of multispectral imaging is new. It takes time and care to image ancient scrolls, art, and documents, and researchers are just starting to uncover what history tried to erase. I hold out hope that somewhere in some dusty monastery or museum collection, more of Hipparchus's work is waiting to be found. Technology. It reveals the past, and sometimes it makes the present a whole lot more exciting. Next up, I'd like to invite on our aerospace correspondent, Eric Mattis, to fill us in on what's gone up this week. Hey, Eric.
Hi, Pamela.
I always worry about January launches. How are things going?
Not great, but it's a pretty good month, all things considered.
Fair enough. What did happen this past week?
Not much, but some pretty cool things did happen. As rockets go, this was a pretty standard week with only 3 launches, but those 3 were an example of just how varied the different types of modern rockets are. The first one to launch, on January 24th, was a commercial Rocket Lab Electron from their brand new launch pad at Mars. No, not the Red Planet, but the Mid-Atlantic Regional Spaceport on Wallops Island in Virginia. One cool fact about that pad is it is entirely contained in the perimeter of the pad for another rocket, the Northrop Grumman Antares. Although Rocket Lab's headquarters are in Long Beach, California, all 32 prior launches have taken place from the launch facility on the Mahia Peninsula in the North Island of New Zealand. This allows them to comply with American regulations and be able to provide launch services to the U.S. government. Their New Zealand launch facility can only reach inclinations between 30 and 100 degrees, slightly retrograde orbit, depending on the direction of launch. Many customers need their satellites in lower inclination orbits that are closer to the equator. So, in 2019, the company started construction of their third pad, this one in Virginia, to reach those lower inclination orbits. They were supposed to launch from the new pad in 2022, but were delayed because of NASA's need to certify their autonomous flight termination system, because NASA is in charge of range operations at Wallops. So, what did this first US launch of an Electron carry? 3 satellites from a company called Hawkeye 360. Hawkeye 360 operates satellites that detect radio signals on the Earth's surface. With multiple satellites, the company can tell exactly where signals come from, what is being sent, and by whom. After collecting this data, they then sell it to commercial customers and the government. The company has plans for a 30-satellite constellation, and with this launch, the company has half of that number in orbit. The launch was successful, and it did not include a first-stage booster recovery attempt, something Rocket Lab is planning on future missions. The next rocket to launch, this past week, was a reconnaissance satellite 2 days later on the other side of the world. On January 26th, a Japanese H-2A launched the IGS Radar 7 satellite. The satellite has a dual role, being used for both the Japanese military and civilian disaster response. Radar satellites are useful for both military and civilian roles, but especially in military applications, because they can provide similar information that optical satellites can, but at all hours of the day and through cloud cover. The final launch of this week was another batch of Starlink satellites for SpaceX's Internet constellation, launched later the same day from Vandenberg Space Force Base in California. Falcon 9 booster 1067 completed its 9th flight, sending 56 Starlink satellites into orbit. The launch and booster landing were both successful, marking the 69th launch of Starlink satellites since 2019. The payload fairings on the rocket were successfully recovered for future missions. From those 3 launches, we can update our launch statistics for 2023. The number of toilets in space is still 9, 4 on the ISS, 2 on the Tiangong space station, 1 soon to be burned up on Soyuz MS-22, 1 on Crew Dragon Freedom, and 1 on Shenzhou 14. We keep track of orbital launches by launch site, also called spaceport. Here's the latest breakdown for 2023. USA 9, China 5, Japan 1. Of those 15 launches, 2 were failures.
Thanks, Eric. The constant march toward a sky full of satellites just keeps marching on. New satellites have to get launched for a variety of reasons. Some missions are simply new ideas being put in orbit. Others are replacements for older missions that bring added technology to old problems. Whatever the reason to launch, these spacecraft have to be designed to withstand massive temperature swings, solar radiation, and cosmic rays. In the future, a new material developed at the University of Surrey may make survival in space a bit easier for future missions, referred to as a multifunctional nanobarrier structure. This nanocoating can protect spacecraft from damage from atomic oxygen and ultraviolet light without blocking the radio signals we use to communicate with missions. In the lab, this material reduced operating temperatures from 120 degrees Celsius to 60 degrees Celsius. And the energy can even be harvested for later use. So far, this material has only been tested in a laboratory. When we know more about its orbital success, we'll bring that news to you here on EVSN. Before we go, I'd like to leave you with this space fact. On January 24, 1986, NASA's Voyager 2 mission flew past Uranus. This encounter allowed researchers to discover Uranus's gossamer rings and to image 5 of Uranus's many moons in detail. As a Gen X kid, I wasn't inspired by the Apollo missions like so many of my colleagues. I wasn't even born yet when the last Apollo mission flew. For me, the Voyager missions created a steady drumbeat of inspiration throughout my childhood. I distinctly remember being yelled at to take a nap in 1979 so I could stay up to see Jupiter data. By 1980, kindergarten me was a bit better behaved, and I remember seeing everything on TV, no yelling about naps required. Despite being a lot older when Voyager reached Uranus in 1986, I don't actually remember when I first saw those images or learned about this blue world's icy moons. Just 4 days after Voyager 2's Uranus encounter, NASA suffered one of its 3 great tragedies. the loss of the Space Shuttle Challenger on January 28, 1986, along with the January 27, 1967 loss of the Apollo 1 capsule during testing, and the February 1, 2003 loss of the Space Shuttle Columbia. These 3 missions have made the last week of January one in which we often mourn NASA's failures. This week, we invite you to instead celebrate NASA getting a good look at Uranus, and also that Mars Opportunity landing we mentioned earlier in our show. January is a good time to check out other worlds. That's it for now. We'll be back next week with more science and rocketry. Good night, and remember to look up.